Hi, today's topic is regular expression, which can define as pattern to match with a specific set of strings, which is kind of language to define that kind of set. And before we cover this, we're going to review last class that was structural induction. Structural induction is generalized induction which use a specific set. The structural induction going through this set. And the set usually defined by the recursive definition. Here we have an example, rooted binary trees. Uh, the basis is a single root node, which is a rooted binary tree as well. And we need to combine with two other rooted binary tree with this root node. We can make another root node like this. And there are two functions to get information about the binary trees. Size will give you number of nodes. Height will give you the how many steps are there from the root node to the root node, which has maximum levels. So when you apply the size function to the root node, there will be 1. When you apply the size function to the new tree with the root node and other two trees, so we have this node, so we can simply find that is a node, and there is numbers of node in those two. We can add them together. We can get all the node number there. And height, if we have a single node, there is no difference between the root to the others, so that will be 0. When you have this tree, so you can simply looking at this step, one step to the root to from the root to other, and maybe we don't know which one is bigger or longer, so we can compute the height for each, then find the maximum to get the final result. So this is the definition of structural induction. So we want to prove claim P of X. So X is a member of the set S. So P of X is true for this numbers or members in the set S. So first we need to find base case. That is to show P of U is true for all specific element U of S mentioned in the basis step for the recursive definition. And then we need to do this inductive hypothesis that assume the P is true for some arbitrary value of each of existing named element mentioned in recursive step. And then we need to do this inductive step, which prove that P of W holds for each of the new element W constructed in the recursive step using the named element mentioned in the inductive hypothesis. Then we can conclude the claim P of X is true. So we can connect these things with the recursive definition of rooted binary tree. So specific elements U will be the root node in the basis. The existing named elements are T1 and T2. The new element W is the new binary tree which has root node and T1 and T2, then construct a rooted binary tree together. And so this is the difference between structural induction and typical induction. The ordinary induction is a special case of this structural induction, which use retrorubber set instead of general set S. Structural induction use general set. So we can define set using this rule basis and recursive steps. So we can make this um, 21 using 6 and 15 with this rule, and this will be kind of multiples of 3, so we can uh, prove this every element of S is divisible by 3. So this is the solution. First we have to define the claim and find base case which is true or not. In the definition, P of X is about the 3 is 3 divides 6, 3 divides 15, so that's why P of 6 and P of 15 are true. And then we can do the inductive hypothesis. Suppose that P of X and P of are true for some arbitrary X and Y in S. Then we can show the P of X plus Y that is coming from the definition, recursive definition. So P of X is true, 3 by X, and so X is equal to 3m for some integer m, and again P of Y is true, 3 divides Y, and Y is equal to 3n for some integer n. Therefore, we can make this X plus Y that is 3m plus 3n, which can be written by 3m plus n. That's why 3 divides X plus Y. So P of X plus Y is true. So the claim 3 divides X for all X in S is true by the structural induction. Okay, this is about the string. We can see the new function about the strings, that there is a number of character in a string. So for the empty string, number of C is 0. There is the string with one string W and C, character C. In this case, we can divide into number of C from the string and plus 1, because C is the character we are looking for. That's why it will be 1. And another W and character A. In this case, there is no C. Definitely it will be 0. We only need to use this part. Okay, this is about the concatenation of two string and ranks of that. So if you have concatenated string X concatenate Y, the ranks will be divided into ranks X plus length Y. So we want to prove that is correct. So the base case is empty string Y is equal to empty string. So for any X that is coming from string set sigma star, if you find this ranks of X concatenate epsilon, so we can rewrite this into these two parts. Definitely empty string has nothing, 0, so this is ranks of X. So we assume that P of W is true for some arbitrary W that is in the sigma star, we want to prove the P of WA is true for every character A of alphabet. So we have these two setting, and then the ranks of X concatenate WA. So by the definition of this concatenation, we can rewrite that is in this, and then A is the character, and so this is a single character. The length will be 1. So we can divide it into this part and the string part, and we know the concatenation can be divided into two separated ranks. So we can rewrite this X and Y. So, in this case, we can find this part will be same to this, and then this shows this and this relation. So that's why the claim is true by the structural induction. Okay, so I've seen this before, and yeah, we can apply this structural induction to find this inequality is true or not. So this is the relation between size and height, and so size of t is less than equal to 2 to the height of t plus 1 minus 1. So we want to prove it. The base case is about the dot root node. Size will be 1 and height is 0. So we can substitute them in the inequality. The size of t will be 1 simply, and this part is 1 again. So they are equal. That's why the P of that is true. Inductive hypothesis suppose that P of T1 and P of T2 are true for some rooted binary trees T1 and T2. The goal is prove P of these three is correct. So let's look at it. So this is left hand side. This will be written in this again by the definition. Right hand side will be like this by their inductive hypothesis. So if we simplify that into this, so anyway, if the we don't know about the T1 and T2, so maybe if we take the bigger one, that will be definitely be greater or equal to this term. So let's do that. And so because of this part and this maximum, the shape is exactly same to this height of the tree we have seen before. That's where we can rewrite that part into this. And again, this is similar to the original definition. So yeah, in this case, we have this, and this will be going into this part with plus 1. Then the shape is same, and this is true. So P of T is true for all rooted binary trees by structural induction.